Hello, welcome to Soil Search classes. The topic of this video is analysis of variance, or what we shortly call it, Anova. Anova is a procedure that can be used to test the equality of three or more means in one test. For example, suppose professors of a university have decided three different teaching methods and they want to find out if these teaching methods produce different results. Let μ1, μ2 and μ3 be the mean scores of all the students who will be trained by these three newly devised methods. To test whether these methods produce different means, we test the hypothesis H0, which is μ1 is equals to μ2 is equals to μ3. That is, all the population means are equal. This is called null hypothesis, and this is tested against the alternative hypothesis that not all the population means are equal, or there exists at least one pair of population means which significantly differ from each other. Now, a question may arise that if the procedure discussed here refers to the population mean, then why it is called Anova? The reason is that the test statistics used two estimators of variances. The analysis of variance actually divide the total variances into different components. In this example, the variation between the scores of students can be divided into two components. First, variation due to different methods, and the second is the variation in scores of students who are studying under same method. Hence, we can say that Anova is a procedure which involves a systematic way of partitioning total variability in the data into a number of components associated with the nature of classification of the data. One-way Anova. In one-way Anova, we analyze one factor or one variable, and the data is classified into different values of this factor. Let us suppose there are k classes or k levels of a single factor or treatment. Hypothesis of one-way Anova. The null hypothesis of one-way Anova is μi is equals to μj for all ij, that is, all the population means are equal. And the alternative hypothesis is not all the population means are equal, that is, there exists at least one pair of means which significantly differ from each other. There are three assumptions associated with one-way Anova. The first is assumption of independence, that is, the samples are drawn from a population which is random and independent. The second assumption is assumption of normality, that is, the distribution on the population from which the samples are selected are normal. And the third assumption is the assumption of homogeneity, that is, the variances of distribution in the population are equal. Let Yij be the random variable which determines the observation under ith factor where I is equals to 1, 2 and so on till k, that is the number of levels, and j is equals to 1, 2 and so on till ni. Here ni is the size of sample I. For simplicity, let us assume that all the samples are of equal size, say m. Hence, Yij represents the jth observation of ith factor, where I runs from 1 to k and j runs from 1 to m. Now, these observations can be also written as Yij is equals to mu I plus Eij, where mu I is the mean of ith factor level and Eij is the random error component. This mu I can be further written as mu I is equals to mu plus Ti, where mu is the overall mean and Ti is the parameter associated with the ith factor only. It is also called ith factor effect. Thus, model can be written as Yij is equals to mu plus Ti plus Eij, where I runs from 1 to k and j runs from 1 to m. This model is also known as effects model. This k level of factors in the experiment can be chosen in two ways. First, they can be specifically chosen by the experimenter. In this, we called fixed effect model. Alternatively, the k-effect model can be a random sample drawn from a large population of factors. Then we call it random effect models. In fixed effects one-way Anova model, we have summation Ti, I is equals to 1 to k is equals to 1, or summation I is equals to 1 to k Ni Ti is equals to 0. When Ni observations are taken for ith factor level, the least square estimates of mu and Ti can be obtained by minimizing the summation of Eij square, which is equals to this. To obtain the estimates, we have to minimize it with respect to mu and Ti. Here, we have also made the assumption that all the samples are of same size. We will get the estimates as mu cap is equals to 1 by km summation I is equals to 1 to k summation j is equals to 1 to m Yij, which is denoted as y double naught cap, and Ti cap is equals to y I naught cap minus y double naught cap, where y I naught cap is equals to the mean of Yij's for one factor, that is 1 by m summation Yij, j is equals to 1 to m. Here, this y double naught cap is the grand sample mean, where yi naught cap is the mean of ith factor level. Now we can write Yij is equals to y double naught cap plus y I naught cap minus y double naught cap plus Yij minus y I naught cap. Squaring both sides, we would get, that is, total sum of square is equals to sum of square between different square